I want to be bluntly honest about this video. This is just looking at a reagent kind of for the sake of looking at a reagent. It is exceptionally synthetically useful. So if you're planning on any kind of synthesis career, yes, this is important, but we aren't really looking at any new or interesting chemistry here. So addition of CN or a cyano group to an individual structure. The cyano or the nitrile, CN-, is a nucleophile. If we were to look at it, it does have some kind of interesting redeeming qualities, and that the negative charge is located on that carbon. The carbon is the nucleophile side because it can't stabilize the negative charge as well, or stabilize the electrons as well as the nitrogen, because the nitrogen is more electronegative. Okay, so thereby the carbon of that becomes our nucleophilic side. Cyanide can be a challenging reagent to work with, particularly as it's shown up above as HCN, because that does form a gas and is highly, highly, highly toxic. So we do have to be careful when working with cyanide compounds. In this particular drawing, as it's shown, really all they're trying to address is that cyanide, that negative, can come in, attack our carbonyl, which is positive, bounce the electrons up, the result of that being that we would now have the cyanide connected to our structure, so C triple bond N, and then we would have the O-. That O- could pick up a hydrogen from solution, and that would take us to our pseudo final product, and we'll discuss that in a second too, of our cyanohydrin. The cyanohydrin is useful because of the next sequence of steps that goes with it, but what we are doing is adding an alcohol. We now have some potential reactivity, which we'll again look at in a second, and we've still kept that alcohol functional group, or that oxygen connected to that carbon, as a potential site for reactivity. So not only are we doing a chain lengthening or a carbon growth by adding a single carbon, but we're also adding in some new chemistry and maintaining chemistry at our core site. So that's kind of cool from that standpoint. The reaction itself is pretty darn slow, because, and a lot of that has to do with our HCN. HCN is a weak acid, not a strong acid. I think the pKa is somewhere around 9. Okay, with such a kind of middling pKa, it's not going to protonate our oxygen to a large extent. It's also not going to deprotonate in and of itself to form our active nucleophile CN-. So what does that mean? Well, if I don't get a large concentration, so no large, and I'll just put the brackets meaning concentration, no large concentration of the cyanide, then means I don't have an active nucleophile in any real concentration. And because I'm not forming a strong enough acid, I don't have anything to protonate the oxygen to make the electrophile that much stronger. So the reaction is pretty slow. Okay, so what could we do to speed this? Well, one option would be to add an acid. If we add a stronger acid, that will protonate the oxygen, making the electrophilic site that much more electrophilic because of that oxygen wanting to withdraw electrons. And even though we have a low concentration of the cyanide ion, our active nucleophile, we've made the electrophile electrophilic enough that we'll get some kind of speeding behind that process. The other option, as we've seen with the acetals, is that we could just throw in cyanide ion. Okay, cyanide ion you usually have to throw in as a partner with something, a counter ion. So we pick a metal and we would throw in potassium cyanide, sodium cyanide, and we now have an increase in the concentration of the active nucleophile. To get that, we're really kind of running it under basic conditions. So really, yes, it can be sped up by either acidifying or basifying our reaction. Right? Kind of like everything in chapter 18. You can speed it by adjusting acidity or basicity. Okay. The last thing I do want to address here is this kind of next sequence of steps saying hydrolysis, several steps. If we go through and look at the changing in chemistry here, really what we're talking about is that cyanide. So let's, for the moment, ignore the alcohol portion of this and look at the structure. If we draw out our Lewis structure, that's what we would have. Okay, why is that important? Well, that's important because what do we have out here? Well, that red and now blue are polar pi bonds. And this whole unit is talking about nucleophilic addition to, well, polar pi bonds, which means if I'm in this environment with water floating around, water as a nucleophile can also attack and break that polar pi bond. Right? In that process, we're now going to end up with water connected to this. Note, just like we had with the acetals, we've got a lot of charges on this. So if we balance this out under acidic or basic conditions, we can kind of mitigate some of that, and we might kind of foresee our structure shifting to something along these lines, okay, where it neutralizes out. Now deciding how this balances is going to, or where this goes, is going to have a lot to do with the ability for each of those individual species or atoms to share electrons or not share electrons, as the case may be. So if we look at the oxygen versus the nitrogen, oxygen is more electronegative. Right now, it is sharing its electrons between two different sources. Okay? The nitrogen is also sharing it between two different sources, but since nitrogen is less electronegative, it could be willing to share them with a third source. Oxygen doesn't want to share, and what we'll end up seeing, and we'll look at the details in a second, so kind of bear with me, we'll end up seeing that oxygen steals electrons from the hydrogen to make a pi bond, which will then shuttle electrons out up here. And in kind of a pattern, or not kind of, it is a pattern that is relevant to this unit, we would form the carbonyl with then eventually the nitrogen out there. And what we've got now is an amide. The mechanism we've worked through is a nucleophilic addition, so it fits within this system. Okay. What's kind of more interesting is that if we compare that amide to where our textbook is telling us to go, the textbook says take it all the way to a carboxylic acid. That chemistry is now looking at the addition-elimination of an acid derivative. That's chapter 20. We haven't discussed that yet, and it's not in this unit, which means that last step you're not responsible for yet. Okay? And Carty acknowledges that you're not responsible for it, and that's why there's these parentheses. Those parentheses are really there saying we haven't talked about this yet, but you will see it. Okay? But you are responsible for that kind of amide system. Okay? So our cyanohydrin, very cool, very useful. The nitrile itself introduces yet another polar pi bond that can continue to react. Okay? So if we were to go through and look at that hydrolysis of nitriles, hydro, water, lysis, cutting. Okay? So we're looking at water cutting of nitriles, can happen under acidic or basic conditions. Either way you do it, you need water present because, like I said, hydrolysis. And what we're talking about is the water reacting, okay, and effectively breaking one of those pi bonds. Okay, that does cause some interesting shuffling within the structure, and we'll look at that mechanism kind of stepwise here to get to that amide. And we'll go through and do the acidic drawing of it. Your textbook has some awesome pictures that I actually have in the subsequent slides. Okay, but we'll look at those in a second. So, starting it off, if we want to do a mechanism with these starting materials to get to this product, Okay, we have to consider how to move. Well, the first thing we should do would be identify the most reactive thing. Based off the reactivity of things, the charged thing is our most reactive. So we have that positive hydrogen. Okay, so I need to react that positive hydrogen with something useful. I could protonate the water. That doesn't take me anywhere useful because the oxygen of our water needs to be connected to the carbon, which means the oxygen needs to be a nucleophile, so protonating the water doesn't help. Okay? What I do note is that in the change of this reaction, that nitrogen picks up two hydrogens. So probably a good first step, since I know the H plus is the most reactive, would be to go ahead and protonate that nitrogen. So if we were to go through and do that, I don't want to draw that huge structure, so I'm just going to call it phenyl, and then make sure I don't have to worry about the chlorine. We'll just delete the chlorine from our drawing. So there's our phenyl, our carbon, triple bond to our nitrogen, which now has a bond to that hydrogen. Nitrogen would now have a positive charge because it just shared those electrons. It does not want to be positive. So what it could do would be resonance, and we could draw something along these lines. The problem with this is we're now showing a positive charge on that carbon. And you might say, well, that's not a big deal. Carbon's better at holding a positive charge than the nitrogen. If we're comparing these two structures as far as Lewis structures, the top one is the better Lewis structure, and that's because all atoms have their octet. All the way back in OChem 1, that's one of the rules for Lewis structure. Best structure has the full octet. But this resonance does call out the reactivity for me. Okay, so while this is best, that says a B, this is probably the most useful. Because as useful, I now see that the reactive site in that best structure isn't the nitrogen, it's the carbon. Which means I can now drop in my water molecule with its lone pairs and have it connect to that carbon. That is going to necessarily break the pi bond. And so we would now move on to our next intermediate. So pH, C, double bond, nitrogen, hydrogen. We'd have the lone pair now on our nitrogen. And we'd now have that new bond between our carbon and our oxygen with its hydrogens and a formal positive. Oxygen doesn't want to be positive. Okay, I'm definitely going to run out of space here. Okay, so a second equivalent of our water, which is our solvent, can come in, remove those electrons. And we would now have kind of our neutral structure. Okay, so cool. That's not our final product, though. Okay, we have to remember that we're still in acidic conditions. The nitrogen can react with a hydrogen. And this can set us up with carbon, oxygen. Our nitrogen was now two hydrogens, which is good, but it's still got the pi bond. Again, we could take advantage of resonance to help us understand something about the reactivity of this structure. And if we bumped out to the resonance, we could see that that nitrogen could steal the electrons from the carbon, picking up a lone pair. The oxygen still chilling out there, carbon with the positive. Okay? Again, that's going to help us out because we need to stabilize that carbon. How could we do that? Well, we could either use the electrons from the nitrogen or from the oxygen. If we use the electrons from the oxygen, whoops, I don't want to draw it on that one. Because by drawing it on that one, I'm saying that is the better Lewis structure. So we could force that out. The result is I'd have pH, C, single bond, nitrogen, my 2 hydrogens. There's my lone pair. I have my double bond now to my oxygen with just 1 lone pair, and it would now be positively charged. Okay? So which way should I go? Should I have the oxygen donating electrons or the nitrogen? If we're just kind of oscillating back and forth between those, okay, we might say, well, and actually, technically what I just drew there was resonance. Okay. We might go through and say, well, between all of those, they're all roughly equivalent. The blue one for sure is bad. Okay. And I'll try and make this one purple. The purple one we might think is less good than our black one. And that's because we have oxygen with a positive charge as opposed to the nitrogen. But what we can add to this is that if we throw in another equivalent of the water, we can now take this to the full-on amide. Okay? So now why would the amide matter? So if we're looking, all of this is really just kind of resonance sitting around in each other. So what we're trying to decide is which would be a better structure, the amide or, I'm not even sure what to call this one, the equivalent of the amide except with a double bond between the nitrogen versus the oxygen. Okay, which one of those is more stable? This again goes back to the characteristics between our oxygen and our nitrogen. Oxygen is more electronegative than our nitrogen. Okay, so we would rather have the electrons more centrally located for the oxygen than for the nitrogen, which would suggest the amide is the better of these two forms. We should be moving through those kind of resonance structures with the acid-base transfer. Okay? I know, lots of stuff floating through there, but if we walk through it, we started with an acid-base reaction, followed by our nucleophilic addition, followed by another acid-base step, followed by another acid-base step, followed by another acid-base step. Okay? So we did lots and lots and lots of acid-base. The sequence in which we did them becomes important depending on the environment that we're located in. This can run under basic conditions. It just changes the overall mechanism. Yes, that's a mess to look at right now, but ideally as we stepped through it, hopefully each of those steps made a little bit more sense, and that's what you should be evaluating when you go through and look at a mechanism, say even in the textbook. Okay? For example, when we look at these, there's our mechanism again. Proton transfer, acid-base, nucleophilic addition, acid-base, acid-base, acid-base. Okay? So when you evaluate that mechanism or consider it when you're looking at it in a book, you shouldn't be looking at the whole process. You should say, okay, how is that a proton transfer? Okay? What utility was that? Now that I've done a proton transfer, what's the next step in that sequence? Okay? That's what you should be doing when you think about a mechanism, not just looking at the whole thing and trying to piece it all together, because you, really arguably you won't. You have to chunk it and see what those individual pieces are to make sure that you're following it in the right sequence and at the right time for those conditions. If we switch it up to base catalysis, you'll notice it gets a little bit shorter, okay? And that's because it's under basic conditions. The basic conditions actually allow for a slightly faster mechanism or shorter mechanism. The reaction itself isn't necessarily faster or shorter, it's just the mechanism or the drawing that we use to describe it. Okay. With that, we're done with our nitrile. We've shown how to add a nitrile to our non-polar pi bond, or sorry, our polar pi bond. And then we've also shown how that we can add stuff to our nitrile itself because it is also a polar pi bond in that carbon nitrogen, which is going to set us up for the next sequence, which is probably my least favorite, which is the polar pi bond of a carbon nitrogen. And all sorts of fun stuff goes out the door when we talk about that. Okay, so with that, we'll go ahead and stop.